Alrighty, good morning everybody, and welcome back to Math 105. Plan for today is we are going to start Standard 12, which means we will be talking about the postulates 4 and 5, which are a little bit different in nature from the first three Euclid postulates. Got my usual office hours on Monday, 10 o'clock and at 2. No office hours today. Do keep in mind that there is a quiz due tonight on Standard 11. Any questions or comments before we get started today? Ready then. So, a consulting statistician and his client sit down together for the first time. Client says, I desperately need your help interpreting this statistical analysis. What are your fees? Statistician says, my fees are $1,000, and that gets you 3 questions answered. Client says, wow, isn't that a little too steep? Statistician says, no, not at all. Now, what's your third question? Okay, so in Standard 11, we talked about Euclid's first 3 postulates. I kind of decided to split up the postulates into 2 standards like this because the first 3 kind of all fit together and had the common theme in that they were all about how do you construct lines and circles. And you may recall postulates 1 through 3 were basically saying you are allowed to use a straight edge and compass to do the things a straight edge and compass allow you to do. Make straight lines between 2 points, extend straight lines so that they become longer, and to draw circles of whatever radius you want, whatever center point you want. Standards 4 and 5, or standards 4 and 5. Postulates 4 and 5 are a little bit different in that they're not concerned with constructing things so much as they are properties of pre-existing objects. And specifically, postulates 4 and 5 are going to deal with angles. So to start off, I thought we could talk about a few more definitions related to what does Euclid define to be an angle, what does Euclid define to be a right angle, and what does Euclid define to be an obtuse versus acute angle. So here's the thing about angles. At the time of Euclid, there was no such thing as degrees or radians or any way of measuring angles to say, this is the number related to the size of this angle. And so, trying to say something like a right angle is 90 degrees doesn't work for Euclid because he has no concept of what does that mean to say a right angle is 90 degrees. Degrees didn't exist. So we're going to have to be a little bit careful at how we define, say, right, obtuse, and acute angles, and that we can't just be making comparisons to 90 degrees, so to speak. So, a few different definitions to start off. First one is plane angle. A plane angle, which later on we're just going to refer to as angle, is the inclination to one another of 2 lines in a plane which meet one another and do not lie in a straight line. So, according to Euclid, you take 2 different lines and you say that they are inclinated to one another, by which he means, I think, they happen to intersect somewhere. So if this is one line and this is another line, Euclid would call this an angle. Just an inclination to one another of 2 lines in a plane. We have 2 lines that meet one another and do not lie in a straight line. And what that basically means is Euclid doesn't like the idea of having straight angles that have 180 degrees. If this is one of the lines and this is the other, Euclid would not count that as a plane angle. So if we look at the definition Would that constitute an angle, do you think, according to Euclid?
I would say yeah, because he doesn't say straight line.
Yeah, if you notice, when Euclid says a plane angle is the inclination of one another of two lines, he doesn't specify the word straight. So even though this is made up of two lines by Euclid's definition, or lines, or that just which have breadthless length, it would still satisfy that we have two lines and they meet up. And to Euclid, that's enough to say, hey, these two, we have an angle, that we have two lines and they incline on each other, meaning they intersect at a point here. So there are some things like this that I would say that Euclid would consider to be an angle, or some things like this straight line where you kind of go, where one of the lines goes from, say, A to B, and another line goes from A to C. This Euclid would not call an angle, even though in your earlier geometry classes you might have called this something called a straight angle. Euclid says, nah, if you just combine them and get a single straight line, then it's not an angle at all. He specifically wants to exclude that, and as we'll see, that ends up being useful for him. So, right angle, since we can't define a right angle to be 90 degrees, it has to be a little bit crafty in it. And it says, when a straight line set up on a straight line makes the adjacent angles equal to one another. Each of the equal angles is right. And the straight line standing on the other is called a perpendicular to that on which it stands. So what does that mean? So what Euclid is saying is he's not defining a right angle as something that has a certain size to it. He's not defining a right angle in terms of the size of the angle per se. Instead, he's saying, suppose we have two straight lines, and here he does specify we have two straight lines making the angle as opposed to just two lines in general, like what we had over here. He's saying that if we have two straight lines, that makes the adjacent angles equal to one another. So in this case, two angles that are kind of on the same, that are on opposite sides of the same line. So let's say this angle and this angle. When a straight line set up on a straight line makes the adjacent angles equal to one another, each of the equal angles is right. So in other words, when these two blank angles are equal, they are right angles. So what word in geometry? Anybody remember a word from, say, high school geometry? How can we describe two angles that kind of, if you added them up, you would get 180 degrees?
Supplementary.
I would say complementary means they add up to a right angle. Supplementary is the one that says they add up to 180 degrees. For Euclid, since Euclid didn't have the notion of degrees per se, For Euclid, he didn't use the word supplementary, but if he had, he would have referred to two angles which are on opposite, which kind of add together, which when added up would give two right angles. And so here we see two angles that are on opposite sides of the same line, not vertical angles, which are diagonal from each other, but on the same side of the line here. And since these two angles are equal to one another, Euclid called those angles right angles. And in doing so, was able to come up with a definition for what is a right angle, something that's equal to the adjacent angle when two straight lines are meeting up. And he never had to use the words and he never had to have any sort of number associated with them, like 90 degrees or pi radians or whatever unit of measurement you want to refer to. He managed to come up with a description that avoided all of that. And if you think about it, using our modern day degree system, if you had two adjacent angles that added up that are on adjacent sides of a line, if we call this one, say, x and this one y, we would know that they would have to add up to 180 degrees. And so if the two angles happen to be equal, we would get x plus x equal to 180 degrees, which would imply that x would have to be 90 degrees. So any angle that we might think of as having 90 degrees would have to satisfy Euclid's definition here and thus be a right angle, and vice versa. But Euclid's interpretation is likely different than the one I'm guessing you've seen before. Any comments or questions about how Euclid defines right angles? In that case, we'll talk briefly about obtuse and acute angles, and then I'm going to make you do the same activity we did last time, where you think of what words did Euclid never actually define. Euclid, pretty straightforward. He would say that an acute angle is an angle greater than oops, I did them all. Doesn't matter the order. Acute angle is an angle less than a right angle. And an obtuse angle is an angle greater than a right angle. Instead of saying less than 90 degrees or greater than 90 degrees, Euclid just directly compares to a right angle and says acute means something that is less than whatever a right angle would look like. Obtuse refers to something that is greater than whatever a right angle would look like. So what I'd like for you all to do now is to take just take a minute or so. I'm going to flip to the second page in the packet. There are a few terms in these definitions, I would say, similar to the ones that we had from the last packet, that Euclid didn't ever actually define. And so it kind of fell upon us to come up with, and so it fell upon future geometers to try and come up with definitions for some of these undefined terms. So I'd like for you to take just a minute and see what terms do you notice appear not to be carefully defined, or that you feel there's some ambiguity about what the definition is trying to say. So are there any terms that you all see that you think are kind of ambiguous just from looking at these definitions?
Well, right off in the second definition of right angles, he uses the word equal. I don't think he's ever defined equal.
Yeah, that's a good point. What does it mean for two angles to be equal? It's sort of the same as saying, similar to back when the previous standard when we said Euclid never defined what it means for two lines to be equal to one another. Same idea here. What does it mean to say that you have a word equal when applied to angles? I would say that what it means for two angles to be equal would mean that you could would be the same as we said for lines. You could pick up one angle, rotate it around perhaps, but not change the size of the angle at all, and you can place it right on top of the other angle in a way that would make them match up perfectly. Same as we said for lines. For lines, that basically equated to they have the same length. For angles, it ends up being there's the same amount of sort of distance between here and here, which is a little bit unclear. It's a little bit less clear what that means when applied to angles as opposed to lines. So I would say angles being equal really just means you could pick one up and put it right back down on top of the other one. What other terms you see that felt are a little ambiguous?
I felt like a lot of the verbs, like in the first sentence when he says, when they meet one another, like a lot of it could be like, you know, it leaves doubt as to whether they have to like intersect, or maybe it's just like, you know, does that count as meeting one another as well, or
something like that?
Yeah, exactly. And then, yeah, and just kind of being picky, but
yeah.
and then also
It's good to, no, I'm glad you're being picky. That is exactly the sort of pickiness I'm looking for here. Yeah, what does it mean? And if we wanted to, we could come up with some really interesting ways in which lines meet up that you might question as an angle. For instance, how are those lines meeting up? And is an angle being formed there? They're kind of equal to each other for a while, but not for the whole thing.
And another doubt is if you had kind of two curves that met each other like this, like if you had two curves that met each other like this, it's technically not a straight line. But at the same time, it would be all one fluid kind of continuum.
Something like that?
An angle, yeah.
A good question. This does not. I would argue that when these meet up, they do not form a straight line. They form a single line, but not a weird S shape, so to speak. Is that something we would want to call an angle? Because I would argue that appears to fit Euclid's definition. In fact, we could come up with all sorts of weird shapes that might satisfy this definition, but that Euclid probably would not want to be able to treat as angles. I feel we could add one word to this definition in a way that would kind of exclude a lot of these cases. What one word could we maybe add to this definition that would say, hey, don't worry about like this case or that case or any of these other weird curvy line cases?
You'd add straight for lines.
If Euclid had the word straight here, we could have kind of avoided a lot of ambiguity about what does it mean. And as we're going to see later on, Euclid never really does anything except for lines meeting circles, or straight lines meeting circles, I should say. Euclid never really does much with angles that are not made up from straight lines. He usually just relies on the straight line angles. Yeah, it's a good observation.
I'm not sure, again, if this is really anything but inclination to one another. I just seems like an odd word, number one, to choose. Angles, the inclination to one another of two lines. So I'm not really sure what he's meaning by that.
That's It's a little bit unclear. I would say that the word inclination was kind of more commonly used by geometers, I would say, in Euclid's day than it is used in modern day geometry. So this is probably more just a byproduct of the times, and that this word has kind of fallen out of use a lot more than it used to be. But you're right. Inclination could mean, do they have to actually cross each other? Could they just beat up in like a T like this? There's a little bit of ambiguity.
And lines can like
The same way as meeting up.
like they can incline toward each other, but then if we don't define meet, they could just not ever quite make it to each other almost.
Oh, sort of like going into calculus mode for just a second here. If you had like asymptotes, if you had like two lines that did something like we're going to go with infinite lines for just a second here. Two lines that get infinitely close to each other but never actually meet.
Because they're inclining toward each other, and like at least the usage are being close to going towards each other, but never quite making it.
That's true. They're inclining towards each other, but they're never quite meeting up. And there's an argument that you could say, could you consider something like this to be an angle if they never actually meet up? Because this is just an angle of 0 degrees, so to speak. Any other terms?
This is kind of finicky, but in the definitions.
Please be finicky.
In the definitions for acute and obtuse angle, we have less than and greater than, but it isn't really specified if that applies to the inclination or rotation versus just getting bigger.
Yeah, I totally agree. In the same way that what it means for two angles to be equal is a bit ambiguous, I think less than and greater than absolutely are ambiguous terms when you refer to angles. If you had defined angles in terms of being able to compare them by the number of degrees, say, in the angle, then yeah, you could say, yeah, clearly this angle is less than a right angle because this angle has about 45 degrees and a right angle has 90 degrees, and the one with fewer degrees is less than, or the one with more degrees is greater than. But we're not defining angles in terms of degrees. So we don't necessarily have a good way of saying, what does it mean to be less than or greater than a right angle, other than just kind of by visually eyeballing the angle and says, this looks like there's more space in here than this angle does. But you're right. We could have just said, maybe we want to say, this big angle is much greater than this little angle just because the lines are so much longer and bigger. There's some sense in which, hey, look, we have a much bigger inclination here than we do here, even though geometrically speaking, from our intuition, we would say these are both right angles, they're both the same size. Any other terms that you all thought were a bit ambiguous?
Just for the right angle, sat up on and then standing on. It's kind of difficult to see.
Yes.
It's just to kind of picture what, like if you didn't know what a right angle was and you were reading this definition, and you said a line sat up on another line.
Yeah, I agree. A straight line is standing on the other. What does that mean? Is standing on, does that mean the same thing as they have an inclination? Like I feel like we could have defined one term for what does it mean for two angles to intersect, and then just use that term intersect in like all these different cases, and it would be a little bit more clear. Euclid's throwing around lots of different language that lots of different terms that we assume mean the same thing, so to speak, but he's sort of using them in a little bit different ways almost.
And I know we talked about this in the last standard, but again, here he repeats the word plane, kind of like a plane figure, and just like in the last definitions, he's never defined what a plane actually is.
Yeah, Euclid never defined a plane. He just assumes we know that plane is going to be some two-dimensional thing. I will mention I did specify plane angle because in some of Euclid's later works, he talks about angles of like, or for three-dimensional objects and greater, like an angle, like in a cube or something, so to speak. That's not something that lies in a plane since it's three-dimensional, but you could still think of it in a similar way to a plane. Since we're only going to really be doing his two-dimensional stuff for the rest of the semester, instead of saying plane angle from here on out, I'm just going to say the word angle. Yeah, I think this gives us a good collection of ambiguities just in these few more definitions. And it may feel silly to just kind of pick on Euclid and try and just pick apart his definitions, but this is something that mathematicians love to do. It's just take a definition and just rip it to shreds, saying, oh, that term's ambiguous, that term's ambiguous, I have no idea what that means. And lighter geometers had to end up with many, many more definitions of what it means, for instance, of things that may feel intuitively obvious, like what does it mean for two straight lines to intersect? Later geometers ended up having to, in general, come up with lots more definitions to be able to talk about all these things. I was teaching a more modern geometry class, for instance, this past spring, and it even came up with very specific definitions of what does it mean for one angle to be less than another angle. And I think the idea ended up being this angle is less than this angle because you could pick this angle up, match two of the lines to each other, and then this line ends up being, and if you do so, you would get something like this. And if you pick this angle up, put it so that the bottom line here is on the bottom line here, then this piece of the angle is in between the two pieces of the two lines making up the other angle. And it was complicated and messy, but it was something that gave a specific way to look at what does it mean for this angle to be less than that angle. Okay, we are ready for the fourth postulate. Euclid's fourth postulate, simply put, just says that all right angles are equal to one another. So in other words, let's say we have something like this. Let's say we have an angle here, A, and let's say we have an angle here, B. We can read the fourth postulate, simply put, if angles A and B are each equal to their supplementary angles, then angles A and B must equal each other. So this one, this is actually the only one of, I would say, of Euclid's five postulates that modern geometers are totally okay with. And so the modern interpretation of postulate 4 is pretty much exactly the same as Euclid's interpretation. If angle A and angle B are right angles, then they are equal to one another. So I'm not going to write out the modern version in this case. How is this postulate different from the first three? It sort of has a different feel to it. Like the first three sort of had a common theme that this one doesn't share. How would you say they feel different from each other?
Well, they don't directly relate to the compass or straight edge. So you could draw an angle with a straight edge, but you couldn't really make sure it was a right angle. You couldn't make sure they were equal, except your eye would have no way of knowing.
So it turns out you can, but it's not obvious how to do so, and that ends up being one of Euclid's propositions later on, is how do you actually construct right angles? You can't, it's not immediately obvious from just, if I hand you a straight edge and compass and tell you, make a perfect right angle for me, it's not immediately obvious how you would use the straight edge and compass to do that. But as it turns out, you can. It's just, I definitely agree though that this is not specifically saying, here is something that you can do with straight edge and compass. That's right.
I'd say like the first three are more like directions, like they're like, you know, in order to draw a straight line, you know, like you can draw a straight line by using this, you know, whereas this is more just a statement of fact, like all right angles are equal to each other.
Yeah, I would agree. And that the first three, if you remember, we said that the first three postulates were constructive. I would not consider this to be a constructive postulate. In that it's not giving us instructions for how to make something. This is saying, suppose you already have two right angles. I'm not telling you how, this postulate's not saying anything about how to construct them. It's saying, suppose you happen to come across two right angles out in the wild somewhere. Then they have to be equal. But it's not specifically saying, here is how you construct a right angle. Oh, and by the way, if you draw any two of these, they are equal. I'd say that postulates 1 through 3 are constructive, but postulate 4, and it'll turn out 5, are not in that sense. So it's definitely different from the first three, which is why I ended up putting it, kind of split it up, standards up, split the postulates up into two separate standards in this way, and that it's already saying, and that it's just saying something about pre-existing geometric objects. I think I asked the question to the packet, what does it mean for two angles to be equal? Anybody remind me, what did we say it meant for two angles to be equal to one another? Although I hope you were taking notes. So we said two angles are equal. This means that you can pick one up and put it down on top of the other, and they would match up. So in other words, Euclid is saying that, hey, you have these two angles, A and B, they're both right angles, they're both equal to supplementary angles. You should be able to pick up this angle A, maybe rotate it a bit. My hand doesn't bend as much as I would like to rotate. And then you could place angle A down on top of angle B, and they would match up perfectly. And by matchup, you could have that that the lines for angle A are bigger than the lines for angle B, or vice versa. The lines themselves don't have to be the same size, but the pieces of the angle that are right where they intersect are going to behave in exactly the same way. It may be the case that if you picked up A and dropped it on B, you get longer lines going out here, but we would still say they match. Does postulate 4 feel really obvious to you?
Well, it does feel obvious, but that's now, I think, because we have the notion of degrees, so it makes sense, whereas for Euclid, since he didn't have degrees, it would have been more of a new statement, because people haven't really, like, I guess, thought about defining it that way before. With his definition, then it's not incredibly obvious with his definition of a right angle.
That's a good way to put it, and I think I would definitely agree with that.
It feels a little obvious because he's saying right angles are equal to one another, but he defined a right angle as adjacent angles equal to one another.
Yeah. Angles A and B could be right angles, and yet they're not necessarily adjacent to each other. A and B aren't adjacent here. It's just that they happen to have other adjacent angles, which if we wanted to, maybe we could call, I don't know, C and D, that they're adjacent to. And so here we have a sort of scenario where A appears adjacent to something, is equal to its supplementary angle. B is equal to its own supplementary angle. And that makes A and B have to equal each other, which is unclear, I would say, I would agree, from Euclid's definition of right angles. If we had defined right angle as an angle with 90 degrees, then, yeah, duh, all right angles are equal because they have the same number of degrees. But based on Euclid's definition, from his definition alone, I don't think it's very clear at all that if A and B are equal to their own supplementary angles, why should A and B have to equal each other? So, I sum up what I just said. Why is this a postulate? From Euclid's definition, of right angles, it's not obvious they must all be equal. It's obvious, though, from the 90-degree definition, but that's not what you would have to work. And postulate 4 is actually going to be one of the ones that Euclid relies on the most. And that he uses, and that lots and lots of his propositions all relate to angles. And other than postulate 5, which is one that Euclid uses a lot less than the first 4, postulate 4 is the only one that we have so far that has anything to do with angles, so to speak. 1, 2, and 3 talk about you can construct lines and circles, but postulate 4 is going to be the main postulate that Euclid uses whenever he wants to talk about propositions that use angles in some way, such as a triangle. The angles in a triangle add up to 2 right angles, 180 degrees. Euclid does have some notion of like amount of that's similar to degrees, as we'll see. He'll say things like these 2 angles have to add up to 2 right angles. By which we could think now and say, oh, he means 90 plus 90 is 180 degrees. But he never uses the numbers, that sort of language. He'll just say they add up to 2 right angles, which, using postulate 4, it doesn't matter what 2 right angles we choose because they're all equal to each other anyways. Any questions or comments on postulate 4? So, modern geometers are pretty okay with postulate 4, even though it's not constructive like the first 3. And they're, for the most part, pretty okay with postulates 1 through 3. As we've seen, modern geometers have put like a new spin on the first 3 postulates, kind of written them in a way to be more precise, and written them in a way to kind of just make it very clear what they're talking about, filling in the gap that Euclid forgot the word unique in postulate 1. But in general, the first 4 postulates are kind of widely accepted as, okay, these are good building blocks to work off of. We're totally okay with having these 4 postulates. We are totally okay with having a geometric system based off of these first 4 postulates. The 5th one is the one that has caused by far the most controversy. And after reading it, you might find out, might know why that is. So the 5th postulate is the parallel postulate, saying that if a straight line falling on 2 straight lines makes the interior angles on the same side less than 2 right angles, the 2 straight lines, if produced indefinitely, meet on that side on which are the angles less than the 2 right angles. It's a lot more wordy than all right angles are equal. I don't want to spend the last 10 minutes just writing this postulate out on the board, because it's a long one. So I'm just going to let you read off of the packet what it's saying. And those of you watching this outside of class, I did post the standard 12 packet, so I encourage you to read along on the packet, which is on Blackboard. That if a straight line falling on 2 straight lines makes the interior angles on the same side less than 2 right angles. So, let me get a piece of chalk. So what that means is, suppose we have a scenario that looks something like this. A straight line falling on 2 straight lines. So let's say these are the 2 straight lines. Make it steeper. So here, we're going to have 2 straight lines. I'm going to mark some points here. This is going to be our point A. It's going to be point B, point C, point D, point E, point F. So here, we have a straight line falling on 2 straight lines. If a straight line falling on 2 straight lines makes the interior angles on the same side less than 2 right angles. So here, when we talk about interior angles, we mean angles that are kind of on the inside of this H shape. And if 2 interior angles on the same side add up to less than 2 right angles, so in other words, if angle ABE, angle good old honest Abe, plus angle BED, bed, adds to less than 2 right angles, 180 degrees if you're using kind of more modern notation. But since Euclid didn't have degrees, he just said 180 degrees, he just treated it as being 2 right angles. If this angle, ABE, plus this angle, BED, add to less than 2 right angles, then the 2 straight lines, if produced indefinitely, meet on that side on which are the angles less than the 2 right angles. Meaning, on this left-hand side here, since ABE and BED, the angles on the left of this line in the middle, since they add up to less than 2 right angles, what this postulate is saying is if we continue both of these lines to the left, the 2 lines would have to intersect, specifically at this point here. And extending the top and bottom lines to the left, would cause them to eventually intersect. When I say angle ABE, I mean the angle where B is kind of the point at which they meet up. A and E are points on the opposite two line segments. So here, ABE means you start at A, you go to B, then you go to E, and that's the angle that that's referring to. So this would be ABE. This one would be angle BED, because you could go from B to E to D to get this angle. What would be a way that we could refer to this angle right here using the same sort of notation?
You could do either EBC or CBE.
Yeah, and I think both of those would work fine. Start at C, go to B, then go to E, or start at E, go to B, go to C. Both of those would be correct ways to refer to that angle. You just got to make sure that the point that the one in the middle is at the point at which the angle is actually formed. What do y'all think of this postulate? Specifically, how do you feel like this postulate compares to the first four postulates?
It definitely seems more like something that shouldn't just be assumed as like a simple thing that we can build off of. It seems more like something that you would use a postulate to prove almost. It just seems much more complicated and not as obvious as the others.
Oh, that's like almost word for word what I would have said. I was going to say what I had planned. That's exactly right. The first four postulates are things which feel intuitive for the most part. Yeah, given 2 points, there's a unique line that goes between them that you can draw. You could take line segments and make them longer, sure. You can draw circles of any size anywhere you want. Yeah, that makes sense. You have a compass. Compass lets you do that. Right angles are equal. Yeah, they all appear to look the same. Postulate 5 is in no way intuitively obvious. If I didn't have I'll be honest, when I first read this postulate, I didn't have a picture to look off of. I had no idea what this postulate was trying to say. I had to look up like a diagram and kind of say, okay, that makes sense. These two angles add up to less than 180 degrees, means if we keep extending these to the left, they'll have to intersect. Which, by the way, if you notice, angles CBE and BEF, these two angles, if we extended these two angles, are going to add up to more than two right angles, because CBE and BEF are both obtuse. And if we extended these two, if the lines out to the right forever, they would never intersect. So if we keep going this way and this way, those are just going to keep getting farther and farther apart and never have to meet up. It's only on the side where the two angles add up to less than 180 degrees where they would have to meet up at a point if we kept extending those lines in that direction. And so postulate 5 is definitely the black sheep of the postulates. And because you're right, this is the one that mathematicians have thought, nah, this can't be a postulate. This should be something that we can prove from the other four postulates. This should be a proposition, not a postulate, because it feels a lot more like the things Euclid would call propositions later on. But it wasn't. This has a name to it. This one's so infamous it has another name other than postulate 5. It's called the Parallel Postulate. And on Monday, we'll talk about why that is. So we are out of time for today. But when y'all come back when we come back on Monday, we'll talk a little bit more about this postulate, including its modern interpretation, because this one has a modern interpretation that's very different. Why is it called the Parallel Postulate, and kind of what is its place in the history of geometry? This one has a special place in the hearts of geometers in terms of how much they hate it. Every weekend, everybody, we will finish Standard 12 on Monday.